So we want to talk very briefly about solving quadratic equations by completing the square. This is one of several methods we have for solving a quadratic equation, and in my opinion, it's one of the funnest, the coolest, I guess, to work with. It also presents some basic understandings that are necessary for us when we talk about a future method, which is solving using the quadratic formula. In order to solve by completing the square, it is important that we go back and discuss factoring for just a minute. You'll notice that the screen is now showing 4 factoring problems. I have these listed as quick review. I would suggest pausing the video very quickly and going back and factoring these on your own, and then restarting to see how I factor them. For myself, I'm going to go ahead and work through these for the sake of keeping the video to a reasonable length. Notice that we have x squared plus 8x plus 16. When we factor, we always walk through a process in our head that I'll describe in a different video. Hopefully you've all are already familiar with factoring enough. If not, you need to go back and familiarize yourself with factoring before you watch this video. But I always walk through the process in my head of looking for a GCF, which this one does not have. I then look for a difference of squares pattern, which this is not. And then I look for trinomial squares patterns. Trinomial squares patterns are always the same in that they begin with a perfect square, something times itself. They end in a perfect square, something times itself. And then the middle term is always 2 times each of these roots. In this case, it's 2 times 4 times x. When I see that, I can tell you instantly that this is going to be x plus 4 times x plus 4, or x plus 4 squared, x plus 4 times itself. I don't want to get in too great of detail on this. If you're struggling with this, you really need to go back and study trinomial squares patterns. But for our sake today, we just want to accept that this will work. I'm going to do the same thing here. This is a x squared. This is an 8 squared. This middle number is a 2 times an x times an 8. Therefore, it is a trinomial squares pattern. When I see that, I instantly recognize that this is going to be an x and an 8 with a minus sign in between, squared. Over here, this is an x times itself. This is an 11 times itself. This is a 2 times x times 11. Therefore, it is a trinomial squares pattern. This is x plus 11 squared. And lastly, this is x squared times itself. This is 6 times itself. The middle term is 2 times 6 times the x squared. Therefore, this is a trinomial squares pattern. This is x squared minus 6 squared. And down at the bottom is just a summary of that, where it says these are trinomial squares patterns. Where you have, there's a big typo, a squared plus 2ab plus b squared is equal to a plus b times itself. And where you have a squared minus 2ab plus b squared is equal to a minus b times itself. Here again, it's just a quick review of trinomial squares, helping us to remember the pattern that's created. Anytime you have a sum times itself, it will always create that pattern. Anytime you have a difference times itself, it will create this pattern. The reason we refresh our memory on that is because when we complete the square, we're trying to find the value that makes a trinomial squares pattern. We're trying to find the value that makes a trinomial squares pattern. So if I had a trinomial and the third term was missing, I have a perfect square here, x times itself. I know I'm looking for a number times itself here, and I know that middle term has to be 2 times x times whatever this number is. Can you spot what that number is? 2 times x times what equals 18x tells me this has to be a 9. That means this is a 9, which means this is 9 squared, or 81. This, by the way, is x plus 9 times itself. See how I did that? Let's do it again. I have x squared minus 10x plus something. In order for this to be a trinomial squares pattern, this has to be something times itself. This has to be something times itself. And this middle number needs to be 2 times the roots. That's 2 times x times this number. Any idea what that number is? In order for me to get 10x in the middle, this number has to be a 5. Meaning the trinomial squares pattern is x squared minus 10x plus 25, or x minus 5 times itself. Now, I do have several more here that I'd like you to try. I would suggest trying this by pausing the video. I would make a suggestion to you before you do that. Notice that this number right here is half the 18, and this number is half the 10. That may be helpful to you as you try these 5. Here again, pause the video and then try these and then restart the video. I'm going to keep going. I know this is x. I know this is 2 times x times something. That tells me that something is 3, which makes this a 9. This is actually x plus 3 squared. This is a b. This is 2 times b times something. That something has to be a 4.5 or 9 halves. That's b squared minus 9b plus 9 halves, which, by the way, is b plus, this is 9/4. b plus 9/4 squared. I'm double checking that because I think I did something weird. Nope, I'm okay. It's b plus 9 halves squared. How about right here? This is m. This is 2 times m times something. That something must be 2, which makes this a 4. This is m minus 2 squared. This is z. This is 2 times z times something. That something must be a 7, which means this is 7 squared. This is z plus 7 times itself. And this last one, of course, is a duplicate, making that very easy. Hopefully that wasn't too bad for you, because I can use this completing the square to solve equations. Notice, if I'm going to solve by completing the square, this first number has to be a perfect square. This last number has to be a perfect square. And what's in the middle has to be 2 times those roots. What I have here is actually not a difference of squares pattern. It is not a difference of squares pattern, because this 2 squared, even though this is a perfect squared, the middle is not 2 times x times 2. The middle is actually 2 times x times 3. 2 times x times 3. Well, that's a problem, because that would mean this would need to be a 3 squared, and this would need to be a 9 in order for this to work. This is the cool part. I'm actually going to force this to become a 9. I'm going to change this so that I have x squared minus 6x plus 4, and I'm going to use the property of equality to add an extra 5. to both sides. Remember, whatever I do on one side, I have to do on the other. Property of equality says I can do whatever I want as long as I do it on both sides. That makes this new equation x squared minus 6x plus 9 equals 5. Notice that now that this is a trinomial square, I can rewrite it in factored form. And now that it's a perfect square on the left, I can square root both sides to get rid of the square, leaving me with x minus 3 equals plus or minus radical 5. This is a fairly simple equation to finish. X equals 3 plus or minus radical 5. Notice this is actually two answers, 3 plus radical 5 and 3 minus radical 5. This is roughly a 2.2-ish, so this would be 3 plus 2.2-ish, so 5.2, and 3 minus 2.2-ish, which is roughly 0.8. I am going to break the video here, and I'll set up a second video. We'll do a couple more examples like this, and then some that are a little more challenging. Make sure you watch the second part as well.